Hello everyone. Now this will be a two-stage compressor with intercooler. Two-stage compressor with intercooler. So this is the diagram that I have got here. Shows you how the intercooler works between two compressor stages. So an intercooler is a mechanical device used to cool a gas after compression. Okay, so that's here. Now compressing a gas increases its internal energy, which in turn raises its temperature. An intercooler typically takes the form of a heat exchanger that removes waste heat in a gas compressor. So waste heat here refers to an unavailable energy. That means the energy which cannot be converted to useful work. Okay, so intercooling, when the compression is performed in two stages with an intercooler between the stages, then the work input for a given pressure ratio and mass flow is reduced. So remember that. So gas turbine cycle with intercooler. So this diagram which I have drawn, okay, you can see the compressor here. We have two stages. One is the high pressure compressor, the other one will be the low pressure compressor. So what happened is A will be taken into the first compressor where it undergoes isentropic compression. And then it will goes into the intercooler with high pressure and temperature, because after the compression stage, first stage, the pressure and temperature usually will be increased. So what happens is when it goes into the intercooler, it undergoes a cooling process. So that means it rejects all the waste heat as what we have mentioned. Then after that, before going into the second compressor stages, the temperature of the A is relatively low, or you can say the temperature might go back to the original temperature or is the same as what we have for the ambient temperature. Then it goes into the second compressor where it undergoes second time isentropic compression. Okay, compressing it to higher pressure. That is the reason why we have multi-stage compressor. What we want is to raise the pressure but not to raise the temperature. So that is why we have an intercooler in between compressor stages. Then after that, this high pressure and temperature A will goes into the combustor or the combustion chamber where it undergoes a constant pressure heating process. Then after that, you have hot gas at the exit here or at the outlet here. Then it goes into the turbine where it undergoes isentropic expansion. Then it leaves as hot gas at state point 6. Okay, so heat supply when intercooling is used is greater than with no intercooling. Although the network output is increased by intercooling, it is found in general that the increase in the heat to be supplied causes the cycle efficiency to decrease, but that this disadvantage can be offset when a regenerator is used. Okay, so when intercooling is used, a supply of cooling water must be readily available. The additional bulk of unit may offset the advantage to be gained by increasing the work ratio. So this is the TS diagram. Now, so when you look at it, when you look into the TS diagram, so you have one constant pressure line, two constant pressure line, and the third one. So this would be the inlet, A inlet, okay, and it undergoes an isentropic compression in the first compressor, and this is due to irreversibilities. You have 0.2 prime. Then it will undergo constant pressure cooling in the intercooler until it reaches the initial temperature as what we have in 0.1. Then it will undergo another isentropic compression up to state 0.4. Okay, so this is for a closed gas turbine unit. For closed gas turbine unit, you can follow state 0.3 to 4. But with irreversibilities, we have state 0.4 prime. So from 4 prime, it will undergo constant pressure heat addition or heating in the first or in the combustor or in the combustion chamber until it reaches its maximum temperature. Then it will go into the turbine where it undergoes isentropic expansion. And then this dashed line here shows that there is a certain amount of irreversibilities that happens during the process. So this will be the actual flow path from 5 to 6 prime. Okay, so that is the TS diagram. So that is only a constant pressure heat addition. This one you can neglect, or you can omit this part here. Okay, if you are referring to an open gas turbine cycle. So the turbine is to drive a multi-stage compressor. So in this two-stage compressor, the turbine is used to drive both the compressor and at the same time to generate network output. So based on the compressor, we know that compressor is in the A side. So we use specific capacity at constant pressure for A. And then there are two stages, so that you have CPA T2 prime minus T1 for this part here, and then plus this section here. That is from 3 to 4 prime. Both we refer to CPA. That means the A side. Okay. So, and from this we can see T1 is equals to T3 in this case. T4 should be equals to T2 and T4 prime should be equals to T2 prime if the pressure ratios between the compressor stages are the same. Then you have 4 equals to 2, 4 prime equals to 2 prime. But then when you refer to this diagram, they are not equal. So the workout is based on the turbine, okay, and that is on the gas side. So you have CPG, the temperature difference, T5 and T6 prime. Heat supply should be from 4 prime to 5. So you will have CPG T5 minus T4 prime. Then the net work out, you can take the work out from here minus the work in. Okay, so the work in, you have to add up both of these compressor stages. Okay, so and then take work out minus this whole thing here, work in, then multiply by mechanical efficiency if we were to consider the frictional loss due to shaft transmission. Okay, that's for this part. Thank you very much. Stay safe. So this would be the second part, or you can call it as part 9. Okay, so altogether there are 9 parts, more than 9 parts. Okay, so this part here we will be dealing with regenerator. So again, such a system is known as a regenerative gas turbine cycle, open unit. So I've shown you the diagram here. This is the diagram that I have drawn. So you have a compressor, turbine, a combustor or a combustion chamber, and a regenerator. So this regenerator here will exchange heat between the hot gas, shown in red, with the cold air. Okay, with the A stream. So it exchanges heat from hot to cold. So what happens here is compressor will take in atmospheric air and increase the pressure and temperature, okay, when it undergoes an isentropic compression or it undergoes a compression process. So what happens is the air will enter the heat exchanger or the regenerator before it goes into the combustion chamber, so that the temperature at the outlet of the heat exchanger will be raised up slightly due to the exchange of heat from the hot gas to the air stream here. So when it goes into the combustor or the combustion chamber, it will undergoes constant pressure heating. Then it comes out and it goes into the gas turbine where it undergoes isentropic expansion. Then you have hot gas flowing out, okay, on this stream here, and then it goes into the regenerator. Again, it exchanges heat with the air that is in the air stream, okay. So, and then it goes out at state point 6. This is an example of a gas turbine cycle, open cycle unit with a regenerator. So in gas turbine engines, the temperature of the exhaust gas here leaving the turbine is often considerably higher than the temperature of the air leaving the compressor. That means here. So this stream here is higher. The temperature of this line here is higher than the temperature of the air stream here. Okay, so therefore the high pressure air leaving the compressor can be heated by transferring heat to it from the hot exhaust gases between these two streams in a counter flow heat exchanger, now which is also known as a regenerator. Now the thermal efficiency of the cycle will be increased as a result of regeneration, since the portion of energy of the exhaust gases that is normally rejected to the surrounding is now used to preheat the air entering the combustion chamber. Now this in turn decreases the heat input, that means the heat supply, thus fuel requirements, okay, the heat input requirements for the same network output. Okay, so here you have work in based on the compressor. So you have CPA T2 prime minus T1. So the outlet here, okay, due to a certain amount of irreversibilities, instead of perfect isentropic, we do have perfect isentropic here since it's open gas turbine unit. So we have a 2 prime due to the irreversibilities of the system. Okay, so we have 1 to 2 prime. So that's why the air compressor work input is taken as CPA T2 prime minus T1. Then the heat supply will be based on 3 before going into the combustion chamber and after the combustion chamber. So you have T4 minus T3. But remember, you have to consider CPG for gas. Then for the work output is also in the gas side. So that is why you have CPG. Outlet of the turbine is 5 prime. Inlet of the turbine is 0.4. So that is why you have T5 prime minus T4. And then the net work out, as usual, take work out minus work in. And then mechanical efficiency to be considered if there is a certain amount of frictional loss due to power transmission by the shaft. Okay. So this would be the TS diagram with a regenerator. So you can see state point 1 to 2 here. This is the compressor part when it undergoes isentropic compression. And this is due to the irreversibilities. And then 2 prime, then to state point 3 here. Okay. That is the outlet of the regenerator. This is the inlet and this is the outlet. Then after that, it goes into the combustion chamber. So you can see here is constant pressure throughout until it reaches state point 4 at the highest temperature. then it will goes into the turbine where it undergoes isentropic expansion 0.5. So if we were to include the irreversibilities, okay, then we will have to take 5 prime instead of 0.5. And this 0.6 here is the hot gases that is leaving the regenerator. If no heat is lost from the heat exchanger to the atmosphere, then the heat is given out. Okay, so what happens here, if there is no heat loss from the heat exchanger, we can say that the total amount of heat received by the air after the compression process is equal to the amount of heat. This is the heat and this is also the heat. Okay, so this heat is referring to the hot gas stream at the turbine exhaust or the turbine outlet. Okay, this is at the compressor, after the compressor in the heat exchanger. This is after the turbine which is in the heat exchanger. So 0.6 is the outlet, and that means the exit of the regenerator. So whatever heat gained by the air stream is equal to the heat loss by the hot gas stream. So this is an energy balance. Okay, so you can usually use this equation here based on the amount of heat received by the air is equals to the amount of heat lost by the hot gas. You would be able to determine actually the outlet, okay, the temperature of the hot gas at the exit of the regenerator. Okay, and the heat exchanger effectiveness. Here we have a definition or term which we call effectiveness. Usually heat exchanger, okay, this term effectiveness will be taken into account whenever we refers to a heat exchanger. So effectiveness is actually defined as the heat received by the air stream before entering the combustion chamber. Heat received by the air stream before entering the combustion chamber divided by the maximum possible heat which could be transferred from the gas in the heat exchanger. I will show you this during the problem solving. Okay, and then in general, the effectiveness would be the CPA T3 minus T2 prime. That is the temperature difference in the air stream in the regenerator. This one is before it goes into regenerator. This is when it comes out from the regenerator. But this refers to the air stream. Remember the regenerator that I've shown you on the previous slide. Okay, so 0.2 prime is the outlet of the compressor and inlet to the regenerator, and 0.3 here it refers to the outlet of the regenerator, and it is still belongs to the air stream, the air side. And here is the difference between the temperature at inlet to the regenerator, between the two inlets of the regenerator. One is the hot gas, the other one is the air. Okay, so this will give you the greatest temperature difference. This actually will give you the greatest temperature difference. This actually is the temperature difference in the air side. Now this happened within the regenerator. Okay, that's for the section for regenerator. Thank you very much and stay safe. Bye. Hello. Now we will be going into problems solving with intercooler and regenerator. So let's say you have the questions here. It's quite lengthy. Okay, so just let us read out the question. A 5,000 kilowatt gas turbine generating set operates with two compressor stages with intercooling between stages. the overall pressure ratio is 9:1. So a high pressure turbine is used to drive the compressor. So let me show you the diagram first. Okay, so from here, okay, a 5,000 kilowatt gas turbine generating set operates with two compressor stages with intercooling between the stages. So you have low pressure compressor and high pressure compressor. So here I have an intercooler which is in between the two stages. So what happens is air will goes into the low pressure compressor where it undergoes isentropic compression. And then due to a certain amount of irreversibilities, you have 2 prime. And then it goes into the intercooler where all the waste heat, or not all, most of the waste heat will be rejected. And so that temperature at state point 3 here will be the same as what we have at temperature at point 1, at state point 1. Okay, so that is the reason why we have an intercooler. So between compressor stages is to raise up the pressure, building up the pressure without having high temperature, because high temperature will spoil the components of the compressors. So we cannot take any high temperature within the compressor. So after that, we have state point 3 here, which the temperature at T3 of T3 is equals to the temperature of T1. Then it will goes into the high pressure compressor where it undergoes isentropic compression. Then it goes into the heat exchanger. This would be the air stream. This will be the hot gas. So again, you have heat exchange from the hot gas to the air. Then you have 4 prime going into the heat exchanger and 5 leaving the heat exchanger or the regenerator. So then it will goes into the first combustor or combustion chamber where it undergoes a constant pressure heating and leaving as hot gas at state point 6. Then it will enter the high pressure turbine where it undergoes isentropic expansion. So this high pressure turbine, the work output of the high pressure turbine is used to drive both the compressor, the low pressure compressor and high pressure compressor. Then it will leave the high pressure turbine going into the second combustor where it undergoes a reheating process. Okay, so therefore you have 7 prime. This is due to the irreversibilities within the turbine. Then it goes into the second combustion chamber. Then it leaves as point 8, state point 8. Then usually this temperature at point 8 usually is equals to the temperature of point 6, otherwise stated in the question. So it will goes into the low pressure turbine at this high temperature, then leave the low pressure turbine. Now during this, in the when it is in the low pressure turbine, it will undergoes again isentropic expansion. Then from there, work is being extracted and then driving a generator or a propeller. So 9 prime as it leaves the low pressure turbine. Now this is due to irreversibilities again. So going into the regenerator and leaving the regenerator as exhaust gas. So from 9 prime, when you look into this line here, from 9 prime to 10, the temperature of the gas is relatively high, very high. So what happened is instead of exhausting the high temperature gas to the atmosphere, what we do is we are going to exchange heat here with the lower temperature airstream. Okay, so now let's look at the question after looking at the diagram. So 5,000 kilowatt gas turbine, so it generates 5,000 kilowatt here, operates with 2 compressor stages with intercooling. So you have low pressure and high pressure compressor with intercooler. the overall pressure ratio is 9 to 1. So the outermost two pressure line in your TS diagram, okay, the highest is 9 and the lowest one is 1. So if the intake temperature, okay, if the intake pressure is 1.01 bar, if the intake pressure of the low pressure compressor is 1.01 bar, then the highest pressure line should be 9.09. Okay, so that is pressure ratio. Now, a high pressure turbine is used to drive the compressors. That is what I have drawn here. High pressure driving two compressor. Okay, so whatever work output you have here would be equals to the sum of work input of the two compressors. If you were to include the mechanical efficiency, so you have to take mechanical efficiency multiplied by the work output of the high pressure turbine and then equate to these two work input. Okay, usually both these work input would be equal. Okay, if the pressure ratios are the same between the compressor stages. Now, the temperature of the gases at entry of the high pressure turbine is 650. So plus 273, it will be 923 Kelvin. So that is state point 6. And the gases are reheated to 650. That is state point 8. Okay, where it is reheated to 650, which is again 923 Kelvin. After that, it expands in the first, okay, sorry, after that, it will exhaust, the exhaust gases will leave, so will go into the low pressure turbine and leave the low pressure turbine, okay, and then going into the heat exchanger. So in the heat exchanger or the regenerator, heat is exchanged, okay, from the hot gas to the air stream, from the hot gas stream to the air stream here. Okay, so the compressors have equal pressure ratio. So these compressors here, they have equal pressure ratios, which I will show you in your TS diagram. And intercooling is complete between stages. Now the air inlet temperature to the unit is 15. So here the air inlet is 15 plus 273, so it becomes 288 Kelvin. So, and then the question has given us the isentropic efficiency of each compressor stage is 0.8. So each is 0.8. And then the isentropic efficiency of each turbine is 0.85, these two. Okay, the heat exchanger thermal ratio, I will define thermal ratio afterward, is 0.75. The mechanical efficiency is also given as 98% for both power shaft and the compressor turbine shaft, neglecting all pressure losses and the changes in kinetic energy. Then the question asks us to calculate the cycle efficiency, the work ratio, and the mass flow rate. So remember, power is given. There's a reason why the power is given. So for A side, Cp is 1.005 and gamma taken to be 1.4. And for the gas side, the Cp is taken as 1.15. And the gamma, that is the specific heat ratio or the adiabatic index, is taken as 1.333. Neglect the mass of fuel. So the next page, I'm going to show you how to solve the problem. So first, remember, the schematic diagram is very important. And then you have this as the TS diagram. So remember, this is the head part and these are the tail. So the question told us that they have equal pressure ratio. So that means P2 over P1 should be equals to P4 over P3. Or from here, since they have equal pressure ratios, so the temperature and the temperature of one, since temperature of state point 1 and state point 3, they are the same, then 2, 4 will be the same, 2 prime and 4 prime would also be the same due to equal pressure ratio. Okay, so then from 4 prime to 5 is when it goes into the heat exchanger, 4 prime to 5 here. So that is here, 0.5. Then from state point 5 to 6, that is where you have your first combustion chamber. at the highest temperature here, which is 923 Kelvin, if I'm not mistaken. And then it will goes into the turbine where it undergo isentropic expansion, irreversibility. Then after that, it goes into the second combustion chamber here, where it is being reheated to the same temperature 923 as stated in the question. Then again, it undergoes isentropic expansion for the last time, and this is due to irreversibility. And then it will flow, okay, out as state point 10, okay, hot gases or the exhaust. So in the heat exchanger, remember, there will be heat exchange between the hot gas and the air, okay, which is leaving the high pressure compressor before going into the first combustion chamber. So first thing is the pressure ratio. So the question has told us the pressure ratio of P2 is equals P2 over P1 is equals to P4 over P3. The question say equal pressure ratio. So that is what I have written here. And then from here, we can work out that, okay, P4 over P1, that means 4 and 1, or 6 and 9, or 6 with 10, or 6 with 9 prime, 4 with 1, okay, or 4 prime with 1, okay, all of them are having the same overall pressure ratio of 9:1. These are the two outermost pressure line, okay. So, and since they say equal pressure ratio, so you have this, and this is actually the overall pressure ratio. So based on the overall pressure ratio, we can work out based on these two pressure ratio here. So one is P2 to P1, and the other one is P4 to P3. So I've written down in this form. And since P4 over P3 is equals to P2 over P1, that is, since this pressure ratio is equals to this, then you can say both of these will actually give you square. That means the same. When you multiply the same quantity, you have a square. So, okay, we have this. This will be 9:1, the overall pressure ratio. And this is equals to this. Since it is equal, so I can also consider this as P2 over P1. So you have square of this. Okay, so bring the square over, you have a square root of 9. So actually the pressure ratio P2, P1 and P4 to P3 is actually equals to 3. So P2, pressure ratio of P2 to P1 and the pressure ratio of P4 to P3 is actually equals to 3. Okay, so you have to do some tricks here to find out the pressure ratio between 2, 1 and 4, 3. Then after that, you can straight away go into this 1 to 2, which is the isentropic compression. So you can use isentropic relationship here to find out the temperature of T2. Okay, then the next is to find the T2 prime. So usually we have to consider the isentropic efficiency of the compressor. So remember, it's theoretical over actual. So from this, we will be able to find the T2 prime. Then after that, we know that the work input per compressor stages, okay, is given by CPA T2 prime minus T1 or CPA T4 prime minus T3. They are both the same now. Okay, so the compressor work input here is 133.46, and since there are two compressor stages, so the work input you have to multiply by 2. Okay, so the high pressure turbine is required to drive both the compressors as mentioned in the question and to overcome mechanical friction as well, since the mechanical efficiency is given as 98%. So when you look into the diagram, you can see the high pressure turbine is actually driving both the compressor on the same shaft. Okay, so therefore, whatever work output you have here, you have to multiply by 98% and equate it to the compressor, both the compressor work. So that is why I multiply by 2, because one is based on low pressure compressor, the other one is based on the high pressure compressor. So you have the work output by using this Okay, so that is 272.37 kilojoules per kg. The work output of the high pressure turbine can be found by using this method. Okay, why do we find work output of high pressure turbine first? Because we can make use of this to find out the temperature of T7 prime. So based on the work output of the high pressure turbine, remember these are the step-by-step method that I've shown you. So hope it is helpful to you. Okay, so work output of the high pressure turbine CPG T6 minus T7 prime, the high pressure turbine. So we know that the work output of the high pressure turbine is 272.37. So and you can see there's a T7 prime here. T7 prime minus T6, the work output of this. So you can find out T7 prime 686.16 Kelvin. That is T7 prime temperature. So now, once you got T7 prime, you can actually find T7. Okay, so by referring to the isentropic efficiency of the high pressure turbine here. So remember, for turbine is actual over theoretical. So T6 minus T7 prime divided by T6 minus T7 would be the isentropic efficiency of the HPT, high pressure turbine. So we have this. So from here, since this is given, that is 0.85 or something, right? So T6 minus T7. So we can find out T7 from here. So that is the T7. So you have T7 is 644.36 Kelvin. My advice is to have all the temperatures, to find out all the temperatures except 0.10 otherwise mentioned, okay, stated in the question. Okay, or unless we are doing combined power plants, then you might need to find out the temperature of state 0.6, but we are not looking at combined power plant now. Now, isentropic process from the state 0.6 to 7, okay, so that is equals to this. So, what is the reason? Now, the reason is we have to find out the pressure P6, the pressure ratio of P6 to P7, so that we can find out the pressure of P8, P9, pressure ratio of P8 to P9, because we know the overall pressure ratio as well. So since we know the overall pressure ratio, and if we know the pressure ratio between 6 and 7, we will be able to find the pressure ratio of 8 to 9. So from this, we work out, remember for the gas side, the gamma is 1.333, okay? So P6 over P7, you have the pressure ratio of 4.21, this pressure ratio here. So you will be able to find this. So again, you have to use some tricks here. So based on the overall pressure ratio, that is 6 to 9. So you always refer to the outermost two pressure line for the overall, okay? So P6 to 9, I can take P6 over P7, which is this, multiplied by P8 to P9. So, and we know that 8 and 7 are the same. So if let's say, for example, you look at this. Now, since P8 and P7 is the same, we can cancel it out. So when we cancel it out, actually we get P6 and P9, which is the overall pressure ratio. That is the trick, okay? That is the trick. So what we need to do is we have to find out P8 to P9, the pressure ratio. So we know this and we know that, okay? So P8 to P9 pressure ratio, that is our objective, okay? So change it to be our subject. So P6 to P9, given in the question, the overall pressure ratio is 9. And then we know P6 over P7, we don't know P7 over P6. P6 over P7 we have found is 4.21. So if let's say reciprocal, so this will be 1 over 4.21. So from here, we will get pressure ratio of 2.137, that is P8 to P9. Okay, then the next thing is the isentropic process from state point 8 to 9. So from here, we will be able, since we know the pressure ratio already, everything becomes easy. That is to find out the temperature T9 first. So the pressure ratio is 2.137. Gamma, remember, is 1.333 minus 1, so you have 0.333 over 1.333. So that will give you 0.2498. So you get a temperature T9763.13 K. Then after that, the isentropic efficiency, the last part here, to find out the 9 prime. So remember again, actual divided by theoretical for any isentropic efficiencies. For turbine, okay, for turbine. So T8 minus T9 prime here. T8 minus T9 would be here. This is theoretical, this is actual. So from here, we can find out T9 prime. Okay, 787.11 Kelvin. So actually, we have already found temperature 1, 2 prime, 2, 3, 4, and 4 prime. 5. Did we find 0.5 yet? Okay, so we have to yet one more temperature to find. 6 we have found, 7, 7 prime, 8, 9, and 9 prime. All these we have found, 10 no need. Okay, so now we are going to find temperature T5. So how to find temperature T5? So this is the schematic diagram. Now we concentrate on this part here. Now remember the question, in the question they have stated something about thermal ratio, right? So that is this part here and this part here. Okay, so the thermal for heat exchanger, the thermal ratio is actually defined as the temperature difference or the temperature rise of A. Okay, so you don't have to consider the heat this time. That means you don't have to consider the CPA and the CPG. Now you straight away just take the temperature difference. So the simplified of effectiveness thermal ratio by neglecting the CPA and the CPG. So thermal ratio is defined as the temperature difference of the A stream divided by the maximum temperature difference available. So now we are looking at this part here, the heat exchanger. So this is the gas side and this here is the A side. So the temperature difference of the A side would be 4 prime and 5. So since 5 is higher than 4 prime, so we can take T5 minus T4 prime. Then the maximum temperature difference available. Actually, we are looking at the heat exchanger. So we have 5, 9 prime, 4 prime, and 10. So when we take a look at our TS diagram, between these 4 points here, okay, which of these will give us the greatest difference? So you take a look at the TS diagram. So I have drawn here. So this is the highest point, T9 prime here. And this will be the lowest here, okay? Of course, we are looking at the A side. So not to look into the 2 and 2 prime and 4, yeah? We are looking at the actual temperature. So don't look at 2 or 2 prime because that is not inside the regenerator. So we are looking at the regenerator. So you have 9 prime and 4 prime. Okay. Or what about 5 and 10? You can see 5 and 10, the difference is very small. So that will not give you the greatest temperature difference. So the greatest temperature difference when you look at this, okay, you can take T9 prime minus T4 prime. Okay. So then this is defined. And then they have given us a thermal ratio of 0.75, right? So from here, we have got this, we have got this, and we have got this. So we will be able to find out the T5. Okay. So T5 will be 695.53. Now we have completed finding out all the temperatures. And let us table it up. Okay, so I put every temperature here in the table. So you don't have to search one by one. Okay, because it will be time consuming. So the next part is to find out work in, work out, network, and all those stuff. To find out gross work, to find out cycle efficiency, and to find out the mass flow rate. So look here. So network, okay, as I've told you, okay, you can add these two turbines together, the work out and this work out, minus both of these work in. Actually, you will get the net work out as equals to the work out of the LPT. So take the work out of the LPT multiplied by mechanical efficiency will give you actually the net work out. So CPG T8 minus T9 prime, the low pressure turbine is your power turbine. Then multiply by mechanical efficiency because you can see there's a shaft here. So multiply by mechanical efficiency, 98%, which is 0.98. So first thing you get is your network output. Then the heat supply, don't forget there are two combustion chamber. Okay, so one of these is here, the temperature difference. The other one is the temperature difference between 7 prime and 8. Okay, so you have CPG and CPG both are combustor and they are on the gas side. So that is why CPG and CPG T6 minus T5 and T8 minus T7 prime. T8, this is 0.8, this is 0.7 prime. This is 0.6, this is 0.5. So 6 is higher than 5, so that's why I take T6 minus T5. And temperature of 8 is higher than 7 prime, so that's why I take T8 minus T7 prime. From here, you will get the total heat supply, 533.96 kilojoules per kg. Okay, so to find the cycle efficiency, remember, I think hundred of times already, each of the questions in cycles, they are requesting or they're asking us to find the cycle efficiency. So by now, you should be able to remember by heart that is network out over heat supply. So we got our network, we got our heat supply, then we can find our cycle efficiency, which is quite high, 28.68% as compared to the previous examples, okay? So what about gross? Now, the gross work, I have told you what we are looking at. This is the expansion work, both the expansion work, all the expansion work. The gross work here refers to all the expansion work. So the expansion work only at the high pressure and the low pressure turbine. So you have the work out of both. Now, for gross, you don't have to multiply by mechanical efficiency. Okay, gross means the total. Okay, work out CPG T6 minus T7 prime. Okay, first one. And then CPG T8 minus T9 prime, the second one. So that will give you the gross work. Remember, both are gas side, okay? So that is 1.15. So this will give you the gross work. Then the work ratio is defined as net over gross. So we have got our net, and then we have got our gross. So the work ratio is 0.357, which is also quite high as compared to all the previous examples that we have done. Okay, then based on electrical output, that what is given in the question is 5,000 kilowatt, right? So power net, remember to find power net, we have to take network out, multiply by mass flow rate of air, not fuel, okay? We neglect the mass flow rate of fuel. So we have this, and we can find out the mass flow rate of the fuel, which is 32.64 kg per second. I think this example is very long. Yeah, and I think that's the end of the problem solving. And I would like to say thank you and stay safe, everyone. Remember, stay safe. Bye bye. Okay, see you next time.